Welcome, deep divers. So, imagine this. A huge online gaming platform, right? Millions of players.
Yeah, quite the operation.
And their whole success relies on, like, surgical precision, getting those heavy-duty game rendering pods onto expensive GPU nodes
Hmm.
while making sure, sensitive user data pods stay locked down in specific compliant cloud regions. How do they even pull that off in Kubernetes?
That's the million-dollar question, isn't it?
It really is. So today, we're diving deep into the tools that make it happen. Node Affinity, Taints, and Tolerations. It's all about wrestling back that control from the default scheduler.
Yeah, moving beyond just letting Kubernetes guess.
Exactly. Achieving that, optimized, compliant, and reliable setup.
And what's really striking is how these rules, which seem kind of simple on the surface, can stop huge problems. We're talking resource waste, performance hit.
Our clients' nightmares even.
Oh, absolutely. In today's Kubernetes world, clusters are messy, diverse. You've got all sorts of workloads. Understanding this fine-grained control, it's not just nice anymore.
No, it sounds essential.
It really is. Foundational for performance, for cost, for just keeping things stable.
Okay, let's unpack these then. These tools that give you that precision. First one. Node Affinity.
Right.
So think of this as like a wish list or maybe requirements you give to Kubernetes,
Yeah, that's a good way to put it. Preferences or hard rules.
guiding it to schedule your pods onto nodes that fit certain criteria. Could be hardware, like those GPUs for the gaming pods,
Or SSDs, maybe.
or location, like a specific cloud region for that user data, or even just custom labels you stick on nodes, like high memory or something.
Exactly. It's about pulling the pods towards the nodes you want them on.
Okay, so if Node Affinity is about attracting pods,
hmm
what about taints? You said they're kind of the opposite.
Yeah, almost. Taints are more like putting up a keep out sign directly on a node.
Ah, okay.
A taint basically repels pods, stops them scheduling there. Unless, and this is key, unless the pod has a matching toleration, taints are great for reserving nodes, like those pricey GPU nodes for the gamers.
Right, keep the riffraff off.
Sort of, yeah. Or just restricting access generally. Dedicating hardware.
Which leads us perfectly into tolerations. These go on the pods themselves.
That's right, directly in the pod's configuration.
And a toleration lets a pod ignore the keep out sign.
Exactly. It's like having a special pass. It overrides that taint, allows that specific pod to run on what's otherwise a restricted node.
So back to the game example. The rendering pods get the toleration for the GPU node's taint.
Precisely. That's how they get exclusive access.
Now, you might think, Kubernetes just handles scheduling, right? It does its best.
It does, but best effort isn't always good enough.
Especially not for, serious enterprise stuff. Performance, cost, regulations.
Yeah. That's where the why comes in. Why are these features so critical, especially when things get complex like that gaming platform?
Right, why bother overriding the scheduler?
Well, think about it. Without this, your fancy rendering pod might just land on a weak CPU node.
Ugh, terrible performance.
Exactly. Or your sensitive user data pod ends up deployed in a region you're not supposed to use for compliance reasons.
Oh, it's bad.
Very bad. These tools make sure your apps run on the right nodes, avoids poor performance, avoids resource fights between pods.
And the reasons just keep piling up, don't they? Like optimized resource utilization. Node Affinity is key there.
Definitely.
Making sure, say, AI workloads in that gaming platform actually run on nodes with GPUs. You avoid bottlenecks.
And you avoid waste. Paying for a GPU that's running a web server is just painful.
Totally. Then there's workload isolation. Taints and tolerations seem perfect for that.
Yep. Reserving those GPU nodes just for rendering, or stopping, random batch jobs from landing on your critical database nodes.
Keeping things separate and stable. And you mentioned compliance and locality too.
Crucial. Remember those user auth pods? Node Affinity can lock them into a specific region. Data residency laws, lower latency.
Makes sense.
Yeah.
And what about just managing the cluster itself?
Cluster management. Yeah, taints are great here. You can taint your control plane nodes, for example.
So regular apps don't accidentally overload them.
Exactly. Protects the brain of the cluster, improves stability overall.
So it really boils down to flexibility and control, giving admins that fine-grained power, balancing the automation with custom needs.
Precisely. It lets you tailor the environment.
And what happens if you don't use these? What's the flip side?
Well, the flip side is chaos, potentially. Like I said, your CPU-heavy job lands on a weak node, crawls along.
Yeah.
Or, conversely, those expensive ML nodes you bought, They get swamped with totally unrelated pods. Everything slows down, resource contention.
It's like owning a sports car but being stuck in traffic.
Exactly like that. You've got the power, but it's choked because things aren't routed correctly.
Okay, I get the why. So let's get practical. How do you actually do this? How does it look in the config files, the YAML?
Right, let's look under the hood.
How do these actually influence scheduling?
It starts with labels and rules in your YAML definitions. For Node Affinity, first step is labeling your nodes. Key value pairs. Simple stuff.
Like hardware queue.
Hardware queue, region UCs, disk, whatever makes sense for you.
Yeah.
Then, in your pod spec, you define affinity rules.
And these rules refer back to the node labels.
Yep. They say, I want nodes with these labels, and you get two main types, two flavors of affinity.
Right.
There's prefer during scheduling, ignore during execution. That's a preferred or soft affinity. It tells the scheduler, hey, I'd like to run on a node with this label if possible.
But if not, it's okay.
But if not, yeah, it'll schedule elsewhere if it has to. It's a suggestion. Then there's required during scheduling, ignored during execution.
That sounds more serious. Required affinity.
It is. It's a hard requirement.
Yeah.
Schedule me only on nodes matching this label. Full stop.
And if no nodes match?
And then the pod just waits. It won't get scheduled. It stays pending.
So it sounds like required gives you the ultimate control, that precision we talked about. Why would you ever use preferred? Seems less effective.
Ah, that's a really good point. It's all about trade-offs, you know?
Okay.
Required gives you that guarantee, yes. But like you said, if no matching nodes are available, maybe temporarily during an upgrade or scaling event, your pod is stuck, dead in the water.
Right, pending forever, potentially.
Exactly. Preferred gives you more resilience. Maybe you have a batch job that runs faster on a GPU, so you prefer that.
But it can still run okay on a CPU if needed.
Precisely. Or maybe you prefer a certain low latency region, but, you know, if that region's full, getting scheduled in a slightly higher latency one is better than not running at all.
Ah, okay. So it balances the ideal versus, well, just getting the job done.
Yeah, balances performance goals with availability. Makes a lot of sense for less critical workloads.
Got it. Okay, so that's affinity, the attraction. Now, repelling with taints. How do those show up in the config?
So taints go on the node object. You apply a taint with 3 parts. A key, a value, and crucially, an effect.
An effect? What kind of effects?
There are 3 main ones. NoSchedule is the most common. It means no new pods will be scheduled onto this node unless they tolerate the taint.
So it stops new arrivals.
Yep. Then there's PreferNoSchedule. That's softer. The scheduler will try to avoid place the pods here, but if it really has to, it might.
Kind of like preferred affinity, but for repulsion.
Sort of, yeah. And the third one is noExecute. This one's stronger.
How so?
noExecute not only blocks new pods like noSchedule, but it also kicks out existing pods already running on the node if they don't tolerate the paint.
Whoa, okay. Eviction. So what's the real difference in practice between noSchedule and noExecute? That sounds pretty major.
It is. It's quite significant. Think of noSchedule like putting up a temporarily closed sign. No new customers allowed in, but the ones already inside can finish their meals.
Okay.
noExecute is more like a fire alarm and immediate evacuation. Everybody out now unless you have the specific safety pass.
Wow.
Any pod on that node without the right toleration gets evicted. It's often used if a node is having problems like disk issues, or if you need to drain it for maintenance quickly. Gets rid of incompatible workloads fast.
So if a node has dedicated critical, noSchedule,
then only pods with the toleration for dedicated critical can be scheduled there going forward. Existing pods without it are fine.
but if it was dedicated critical, noExecute.
New pods are blocked, and any existing pods without that toleration get kicked off.
Gotcha. And the tolerations themselves, those go in the pod definition.
Exactly, right in the pod spec. The pod lists the taints it's willing to tolerate, matching the key, value, and effect of the node's taint.
So it's the pod saying, yeah, that keep out sign, I have the pass for that one.
That's it perfectly. So our game rendering pods list the toleration for the GPU node's taint, and boom, they get access.
What seems really cool is using them together. Combined usage.
Oh yeah, that's where the real power comes in. They aren't mutually exclusive at all.
So you could have, say, a machine learning pod for that gaming platform. It could use a required affinity for hardware queue.
Making sure it only even considers GPU nodes.
And also have a toleration for, say, role ml.noSchedule.
Which lets it land on a GPU node that's specifically tainted and reserved only for ML tasks.
So it ends up only on GPU nodes and only on the ones set aside for ML. That's super specific.
Exactly. Hits all the right criteria. Right hardware, right isolation group. Very powerful combo.
So if we try that analogy again, Node Affinity is like choosing your preferred type of restaurant.
Yeah, maybe I want Italian tonight.
Taints are like the reserved for private party sign on a whole section of that restaurant.
Mm-hmm. Keeping the general public out.
And tolerations are your actual invitations to get into that specific private party.
Spot on. That's how you get your special ML pods into the reserved ML section, even though it's closed to others, or your database pods onto their dedicated isolated tables.
Okay, so stepping back, the overall scheduling process is the Kubernetes scheduler juggling all this.
Yep, the scheduler is the brain doing the calculations. It looks at all the node labels, the pod's affinity rules, all the node taints, the pod's tolerations.
Lots to consider.
A fair bit, yeah. It uses affinity to figure out the attractive nodes and then uses taints and tolerations as a filter.
Filtering out nodes the pod can't go on, or filtering out pods that aren't allowed on certain nodes.
Exactly. It's its constant evaluation to find the best valid placement based on all these rules you've set up. It's a continuous process.
Right. And there you have it, deep divers. The pretty amazing power and, well, precision you get with node affinity, taints, and tolerations in Kubernetes.
Yeah.
It really is about bringing that intelligent order to your cluster, taking it from just, a bunch of computers.
Something much more tailored and efficient.
Yeah, a highly optimized, really purpose-built environment for your apps.
And if you connect that to the bigger picture, really understanding how these pieces fit the node labels, the different affinity rules, those taint effects, no schedule, no execute, and how tolerations act as the passkey.
All orchestrated by the scheduler.
Right. Getting that is just fundamental, really, to optimizing how you use resources, making sure you meet compliance rules, and just keeping the whole thing stable, especially when your clusters get complex and diverse.
It's how you make sure your infrastructure is actually working for you.
Instead of fighting against it. Absolutely.
So here's something to mull over as you go about your day. Given all this fine-grained control we've talked about, how would you even spot that something's wrong? How might you identify unexpected allocation issues if maybe these rules weren't quite right in your cluster?
Good question. Where would you start looking?
Yeah. And once you did spot a problem pod's not landing where you expect or nodes being underutilized, what would be your absolute first step to troubleshoot it? Something to think about. Until next time, keep diving deep.